Bon après-midi tout le monde. Good afternoon, everyone. It's my pleasure to present a year-end update on our project entitled Cumulative Effects of Resource Development on Mining Impacted Watersheds. The watersheds we're interested in are in the historic cobalt mining district in northeastern Ontario. So when you're assessing the cumulative environmental effects in a historical mining district such as cobalt, which is undergoing a new exploration boom, several scientific questions come up. Perhaps first and foremost is how do you go about assessing environmental impacts from new resource development against a brownfield legacy of pervasive contamination? Another key question is, what were the pre-mining geochemical baselines in soils, sediments, vegetation, and waters in watersheds that were naturally mineralized beforehand? Another interesting question is, can lake sediment cores provide a reliable chronology of different phases of resource development in a mining impacted watershed? And finally, what are the effects of climate change on environmental assessments? So task one of our project is concerned with metal or metalloid loadings in groundwater discharging to surface waters. And in particular, we're interested in anthropogenic discharges of mine impacted groundwater, such as you see in the photo on the right, which shows mine water coming out of shaft 98 of the Nipissing mine in cobalt. The research question here is concerned with establishing or identifying the relationship between the concentration of mine water and the flow rate at which it discharges for these point sources of mine drainage. The interest here is, can we predict concentrations that will be associated with extreme flow events in the future related to climate change? So this fiscal year, we completed high-frequency monitoring of flow and chemistry of waters discharging from shaft 98, and the analyses of the water chemistry were also completed. And here are some results. In blue, you see the hydrograph of mine water discharge with a peak there in the spring freshet of 2022. In red, with a scale on the right, you see a chemograph for arsenic. And what's interesting here is that the peak arsenic concentration lags the peak flow rate by a little bit over a month. Looking now at cobalt, we see that peak cobalt concentrations in red lag by only a lot less the peak flow rates. So clearly the dynamics of cobalt and arsenic mobilization are different, and we're trying to understand why. Turning now to task two, which is concerned with the legacy contaminants in wetlands and lake environments. And this task is led by Mike Parsons. It involves the sampling of mine waste, sediments, and surface waters, both upstream and downstream of mining impacted areas, to evaluate concentrations and speciations of metals of interest in both pre-mining and near surface sediments and pore water. And the photo there shows Mike and some colleagues out on the ice of Lake Temiskaming taking lake sediment cores. This past year, we completed geochemical and geochronological analyses on some of these cores from Lake Temiskaming. This involved logging 9 sediment cores with a variety of tools, including X-ray computed tomography and PXRF. Over 400 sediment samples were sent to ACT Labs for analyses by ICP-MS, and a few subsamples from 3 cores were submitted to INRS for radiometric dating. Now, the results of these analyses will be used to assess pre-mining baseline concentrations of key elements of concern, the influence of past mining activities, and the extent of post-mining recovery. And I'll show you some pretty neat results on the next few slides. Here we see arsenic concentrations in sediment cores for 7 deep water core samples. The locations of the core samples are shown in the map inset of the west shore of Lake Temiskaming, and these samples were obtained in deep water. I'll point out also the location of the outlet of Far Creek and this shallow shelf area where another series of core samples were obtained. Now, these arsenic profiles really show nicely the onset of mining activities in the Far Creek catchment. And their arsenic shows a number of spikes for perhaps related to different periods of activity. But the arsenic concentrations also recover back to baseline values near the top of the cores, which suggests that some sort of natural passive restoration. Now here we see metalloid concentrations for different elements in a shallow water core sample taken from the shelf area on Lake Temiskaming. And a photo and X-ray tomograph of the core sample are shown on the left. And what we have there at the bottom of the core are varved sediments overlain by what appears to be massive tailings and then capped again by varved sediments. And this stratigraphy is really nicely reflected in the metal concentrations. We see a very sharp uptick in metals at about a depth of 75 centimeters in the core, and a gradual tapering off of the concentrations near the top of the core. We also see here concentrations measured by PXRF in the solid dots and ICP-MS in the empty dots. And clearly PXRF does not give a very good estimate of ICP-MS concentrations, but nonetheless, PXRF measurements were really useful in identifying qualitatively zones of potential contamination. Turning now to task 3 on the mineralogical characterization of mine waste and other solid phases, led by Jean Percival. Under task 1, we completed geochemical analyses of Crosswise Lake tailings core using both aqua regia and total digestions. In this, we were provided some funding from the Critical Minerals Program. We also continued with our interpretation of mineralogy in Crosswise Lake tailings and with a study of heavy mineral separates in other tailings core samples. Here we see depth profiles in tailings boreholes of silver. And in red, we have concentrations with an aqua regia digestion, and in blue, concentrations with total digestion. And we see that sometimes there are big differences between the two, which suggests that sometimes the silver is hosted in more refractory minerals. We also note that there's some pretty high silver concentrations between 2 and 3 meters depth within the boreholes. Here we see depth profiles for cobalt in these cores. And in this case, concentrations measured with aqua regia and total digestions are essentially equal. However, one interesting thing to point out is the very high cobalt concentrations at the bottom of borehole 03. And looking at the core with the naked eye, you can see why. It's chock full of erythrite, which is a well-known secondary mineral associated with cobalt arsenides. And here I'm showing you a highly magnified image of erythrite crystals from the sediment, from the tailings rather. I won't say much about the analysis of heavy mineral separates other than the fact that we've identified a host of minerals, including native bismuth, arsenopyrite, erythrite, pyrite, etc. Turning now to task 3.3, which is concerned with the micromineralogy of primary and secondary arsenic, cobalt, nickel, and antimony phases in the tailings. This year, Queen's University student Melissa Chapcut, co-supervised by Heather Jameson of Queen's and Michael Parsons, successfully defended her master's thesis, which was entitled Characterization of Tailings, Sediments, and Vegetation and Their Impact on Metalloid Mobility in the Cobalt Mining Camp. Melissa went on to present her research at a conference at the GACMAC 22 conference in Halifax. Here are some results from Melissa's work. The photo on the left shows horsetails growing in tailings at one of the mines in the cobalt area. The middle photograph shows parts of a horsetail, including the roots, the rhizome, and the shoots. And the SEM image on the right shows iron plaque coating the horsetail roots. And Melissa found that metalloids, such as arsenic, are preferentially concentrated in the roots of horsetails on these iron plaques, making horsetails potentially suitable for phytostabilization of mine wastes. Now, finally, task 5 of the project is concerned with weathering processes in cobalt-type silver, nickel, cobalt, arsenide tailings, and this task is led by Tom Al at the University of Ottawa. Well, Tom's student, Cole Fisher, successfully completed his master's thesis this year, which was entitled Mineralogical and Hydrogeochemical Characterization of Legacy Mine Wastes near Cobalt, Ontario. And this work was presented in a talk given by Tom at the 2022 GACMAC conference in Halifax. And that concludes my update for this year. So thank you very much for your attention.